Okay, so it's my pleasure to introduce Kristen Hendricks from Rutgers. And sorry, one second. And she's going to tell us about a surgery exact triangle for involutive Heegaard Floer homology and consequences. So take it away whenever you're ready, Kristen. And I'll send out a link in just a second for notes for people who want to follow along.
Great. So I guess I'll share my screen. Great. Okay, now I'll share my screen. Okay, thanks so much for having me. It's a pleasure to be here. I've really enjoyed talks in this seminar in the past few months. So today I want to tell you about, this is a symplectic geometry seminar. We're going to talk about an application of symplectic invariance to low-dimensional topology. So we're going to talk about a surgery exact triangle for a theory called involutive Heegaard Floer homology. And the first thing to say is that this is joint work in progress with Jen Hom, Matt Stoffregen, and Ian Zemke. Okay, so what are we going to do? First, we're going to talk a little bit about the homology, background on the homology cobordism group. Then we're going to talk about Heegaard Floer and involutive Heegaard Floer, perhaps from the perspective of a symplectic geometer. And then we're going to talk about why exact triangles and surgery computations. So at the end of part 1, we'll have stated some theorem, and in part 3, we'll talk a little bit about why it's true. Okay, so with that in mind, let's get started. So background on the homology cobordism group. So we talked a lot about H-cobordism earlier today, but now we're going to talk about homology cobordism. Okay, so let's recall. So what are we studying today? We're studying three-dimensional manifolds. So maybe I have Y1 and Y2 are closed-oriented three manifolds, and they're, okay, I can minimize that, great, are homology cobordant. Written Y1 equivalent to Y2. If there exists a smooth compact Floer manifold connecting them, with the property that inclusion on either end induces an isomorphism on homology. Okay, so if I allowed any old cobordism, that wouldn't be very interesting. All three manifolds would become equivalent. If I looked at homotopy cobordism, that also wouldn't be very interesting because the first homotopy group comes very close to determining the three manifold. You can make a short list of examples for which that isn't true. It turns out homology cobordism is in this nice range where some interesting equivalences happen. Homology is nice and flexible to work with, but there's still lots of cool information contained in the relationship. So let's let theta 3 then be the integer homology spheres. Those are going to be three manifolds with the same integer homology as the 3 sphere up to this relationship. So Y are closed-oriented three manifolds. Same integer homology as the 3 sphere, and we say they're equivalent if they're homology cobordant. And this is not just a set of equivalence classes. This can be given the structure of the group under connected sum. Makes this into an abelian group. Okay, what's the identity? That's S3. How do I take inverses? Well, I said these things were oriented. The inverse is happily exactly the thing you want it to be. Okay, so what are some remarks about this group? So the first thing, let's say, is that in this definition, the fact that I he said I was picking a smooth W4 cobordism is very important. So why is that? Friedman's theorem tells us that every integer homology sphere bounds a contractible topological four-ball. Okay, so the fact that this is an interesting thing to talk about at all really reflects the fact that the smooth and topological categories in dimension 4 are quite different from each other. And a dimension matters here. So what if I tried to make the analogous definition in other dimensions? Well, first, if I tried to define the same thing for theta 1 or for dimension 1 or 2, I get 0. And the best analog of what to do in higher dimensions is to take piecewise linear instead of smooth throughout the definition. And that is also 0 for n greater than or equal to 4. Okay, so let me tell you a little bit about what we know about this group, and then we'll get to what we're going to learn about it today. So what do we know about this group? Okay, well, historically, what did we know? Until the 1980s, not very much at all. Until the 1980s, almost the only thing known about the structure of this group was the existence of the Rochen homomorphism, which is a surjection onto Z mod 2Z. And so an example of a thing that's in the preimage of 1 is the Poincare homology sphere, which is the Beach-Coin sphere sigma 235. Okay, and I was not alive for this part of the discussion, but I am assured that lots of people thought that maybe this would just turn out to be an isomorphism. It was a popular conjecture and definitely on no account would have got you laughed out of the topology seminar. But as it turns out, that would have been wrong. So in the 1980s, gauge theory sort of blew open a number of questions in low-dimensional topology, starting with Donaldson's theorem and proceeding from there. So Van Stern in variously 85 and 90, and Furuta in 90, showed, well, first Van Stern showed that there's a Z subgroup of theta 3, where again I can take the Poincare homology sphere and just look at the n-fold powers of that. And furthermore, indeed, I can put in a Z infinity. There's a Z infinity subgroup in theta 3. Sorry, sometimes we write a Z here, and I'm not writing that because I don't have any other rings in this talk. Okay, and indeed they did this by going through the group of integer homology spheres with ciphered fiber geometry and showing there's a Z infinity subgroup there. So this is the subgroup. Generated by integer homology spheres with ciphered fiber geometry. Okay, so more recently, Frishoff in 2010 showed that theta 3 surjects onto Z. That means it has a Z summand. Let's remember our algebra class. Having a summand is stronger than having a subgroup. So the things that I've written down all make sense together. And once again, we can take sigma 235 to go to 1 in that map. And then some very interesting progress, which sort of motivates what's going to happen in the rest of this talk, is in 2013, Ciprian Manolescu showed there do not exist elements Y of order 2 with Rochlin invariant 1, so things map to 1 under that initial homomorphism under Z mod 2Z, using a version of Seiberg-Witten Floer homology that we'll talk about in just a minute. Okay, and why would you care about such a thing? Well, this was an important question because by work of Galusti, Stern, and Matsumoto from the 70s, okay, so this showed there exist non-triangulable topological manifolds in every dimension greater than or equal to 5. So triangulation is a homeomorphism to a simplicial complex. Everything dimension 3 and below is triangulable. All smooth manifolds are triangulable. There were examples from the 80s of non-triangulable topological Floer manifolds. Dimensions 5 and higher were open. This finished the disproof of the triangulation conjecture. Okay, a reasonable person might say, "What? These are 3 spheres. What does that have to do with dimension greater than or equal to 5?" What should you think when you hear that? It's not that it's not that anything special about special about 3 exactly. There's some obstruction that lives in these groups, but dimension 3 is the only place it can be non-trivial, explicitly because dimension 4 is so much the worst dimension. So you should not think, oh, dimension 3 is super special to 5 and above. You should think dimension 4 is just terrible. Okay, so now it won't, one moment while I get around the Zoom controls to get my pen back. Very good. Okay, and allow me to mention, since it goes with the structural results, something that actually follows from what I'm about to say later in this talk, which is that a recent related structural result is that Dihom, Stoffregen, and Trump in 18 showed that theta 3 has a surjection onto Z infinity, so it has a Z infinity summand, not just subgroup. Okay, so let's ask a few questions about this group. Some of them are going to be things we know about, and some of them are going to be things we don't. So the questions we've been looking at so far are largely things that you could ask about any group. You know, does it have subgroups? Does it have some summand? Does it have, how big is it? Does it have some kind of torsion? So we can keep asking questions like this. Okay, so an example of just a question that we could ask about any group is, does this have any torsion? And no one knows. We don't know of any. Popular conjectures include no, not any with Rochlin invariant 1, but maybe with something with Rochlin invariant 0, and good heavens, I don't know. Other questions. How much are elements of theta 3 divisible? And here the answer is, well, we know some things, but they're very small, and there's lots of questions about divisibility we don't understand at all. All right, and in another direction, I can ask questions about this group that have something to do with the fact that I know this is a group of 3 manifolds up to some relationship. So I can ask questions such as, well, I can ask questions such as, does every class have a hyperbolic representative? Okay, so, and the answer to this is yes. That's a theorem of Meyer's from 83. Okay, so you can find something with hyperbolic geometry in every equivalence class. You could also ask, similarly, does every class have a Seifert-Fiberd representative? And the answer to that question is no. And that's much more recent. That was proved by Matt Stoffregen in 2015. Other sorts of things you could ask include, is every class represented by a surgery and a knot? That's very recently known to be no. That's Narzaki, Szabo, and Taniguchi in 2019. All right. And okay, given that the answer to this question is no, you could ask the question, well, you could ask the question, well, all right, not everything has a representative that has Seifert fiber geometry, but what about the subgroup generated by those things? Is that the entire group or not? So is theta 3 equal to theta 3 SF? Okay, so subgroup generated by those things. Another way of saying that is everything integer homology coordinate to a connected sum of Seifert fibered spaces in whatever orientations. Theorem, no. Okay, so this is today's main theorem. Which is work in progress with the people I mentioned at the beginning of the talk. So no, for example, +1 surgery on the following knot. So a -6,7 torus knot 2 times. If you don't know what these knots are, you can just substitute. There is a knot with the property that, if you like. 6,13 torus knot. And then a 2,3 cable of the 2,5 torus knot. Generates Z in the quotient. Okay, so that's our theorem for today. The integer homology cobordism group isn't generated by Seifert fibered spaces. All right, so great. That ends part 1. And now we're going to talk about the tools we use to show that it's true. And I guess I'm going to pause and ask if anyone has questions they want to ask before I go on. Okay, the audience is very satisfied. How did we come up with that knot? So if you want to, right, and why this knot? Okay, so the story is that we know how to compute. So there's going to be some involution on the knot Floer complex from Heegaard Floer homology. We know how to compute it for torus knots and knots with similar properties to them, and we knew what chain complex we were trying to realize because Dai-Hom, Stoffregen, and Trong gave examples of chain complexes that couldn't be in the linear span of the complexes achieved by the Seifert fibered spaces. And at that point, after that, we sort of brute forced it until we found an example. So we don't have a deep geometric intuition about why this knot in particular is the one that worked. We wish we did, because it would be nice if we could get a Z infinity subgroup instead. And this step right here doesn't generalize super well at all. So we haven't been able to get a family. About the other no, I don't have any good ideas about the other geometries. Okay. Great. So let's talk a little bit about Heegaard Floer and so-called involutive Heegaard Floer. Okay, so earlier I mentioned Manolescu's disproof of the triangulation conjecture. And this used a pin-2 equivariant version. Of the three-manifold invariant Seiberg-Witten Floer homology. Okay, so what's pin-2? Pin-2 looks like two copies of the complex circles. They really should be linked as they sit inside the unit quaternions, but we'll just write them unlinked because that's easier to put on the page. So here's a complex circle with a map between them J, such that Ij is minus Ji, and J squared is -1, so that's pin-2 minus, if you like, for those who care about the different versions, and J cubed lives here. So we have this order 4 element, J. Okay, so this invariant associates, say, to an integer homology sphere some pin-2 equivariant spectrum, called the Seiberg-Witten Floer spectrum, which in some moral sense counts solutions of the Seiberg-Witten equations on Y, and is a modification of Kronheimer and Rutgers S1 equivariant homology. Okay, so we work. Come on. In a Floer theoretic, sister theory called Heegaard Floer homology. Okay, so this is a theory that was developed in the early 2000s by Ozsvath and Szabo. They were trying to study the geometric underpinnings of Seiberg-Witten theory. In particular, they were trying to put together some analog of the Atiyah-Floer conjecture for the Seiberg-Witten invariants, which meant they were trying to produce a Lagrangian Floer construction that would return the same information. And the spaces that we're about to see are the things that sort of naturally fell out when they were thinking about those ideas. So Heegaard Floer homology, and indeed, so Heegaard Floer homology goes through some chain of identifications. Work of Kaluchan, Lee, Tubbs, and Kalan, Ghiggini, Honda, and Tubbs shows that Heegaard Floer is identified with monopole Floer homology. And then work of Lidman and Manolescu shows that monopole Floer homology is identified with Seiberg-Witten Floer homology. And through all these chains of identifications, we're going to be working with something that's identified in various ways with Seiberg-Witten Floer homology. Okay, so we're moving over to the symplectic analog of some gauge theoretic setup that has already been, you're quite right, Paolo, and I apologize. And you taught me how to do that at MSRA and everything. I'm very embarrassed. All right. So we're moving from some gauge theory setup that's already been very successful to its sister symplectic geometry theory setup, where we're going to see other fun things happen. So what's the basic structure of Heegaard Floer homology? Okay, so we're going to have a three-manifold, but actually the three-manifold today will restrict to, say, a rational homology sphere. And to that, we'll associate, this theory comes in various flavors, but we'll associate some CF minus Y, a chain complex, which will be a free, finitely generated, graded F adjoin U chain complex, where F is the field of two variables and the degree of U is -2. And then its homology will be the invariant. So that'll be some finitely generated graded F during U module. Okay, and what does the construction of this look like? So I have my 3 manifold, and I take a self-indexing Morse function on it. And today there will just be one critical point of index 0, one critical point of index 3, some critical points of other indices. And what do? I look at the pre-image of 3 halves. That's a surface of genus whatever the number of critical points of index 1 I have. And I look at the ascending manifolds of the index 1 critical points. These intersect in some circles. And the descending manifolds of the index 2 critical points, which intersect again in some circles. Okay, and actually I think to match the rest of my diagrams, I'm going to do this with 2 critical points instead. All right, and then that information is enough to tell me how to reconstruct the 3 manifold, in addition with a base point, which looks like the intersection of some flow line from the index 0 to index 3 to the index 0 critical point. So now I have this thing, which is called a Heegaard diagram, consisting of the surface, the collection of red curves, which are called alpha curves, the collection of blue curves, which are called beta curves, and the base point. And okay, so you're wondering where the symplectic geometry comes in. To that, I associate a symplectic manifold, which is the G-fold symmetric product of the surface, and 2 Lagrangians, which are, so this is perhaps M. 2 Lagrangians, which are tori consisting of the products of the alpha circles and the products of the beta circles. And then I take a variant of Lagrangian Floer homology to get of that whole setup to get my chain complex. Okay, what do I mean by variant? In the simplest possible setup I could do, I would just delete the base point from the original surface. And then I would end up with a symplectic manifold with Lagrangians that I could take to be an exact manifold with exact Lagrangians, and everything would be very simple. In this case, I'm not doing that. Instead, my differential counts intersections with some divisor given to me by the base point. That's where the variable u comes from. So, and I get a theory over F2 adjoin u. Okay, so you might say, all right, you made some choices in getting to the point where you had a symplectic manifold. How much do they matter? So 2 different Heegaard diagrams for the same, let's say, based 3 manifold are connected by sequences of some set of moves. Okay, so there are some, I can do isotopies and handle slides on the diagram. Among the curves. And these induce Hamiltonian isotopies of the Lagrangians. under reasonable conditions. Okay, and therefore chain homotopy equivalences of the Lagrangian Floer groups. And we can also stabilize the diagram that changes its genus, therefore changes the symplectic manifold that we're working in. But which also induce chain homotopy equivalences. Okay, so that says that this is that says that at least the isomorphism class of the Cepheid join U module is an invariant, and indeed naturality. So the fact that these induce chain homotopy equivalences is approximately Ozsvath and Szabo. And there's a naturality result that says that the sequence of moves between any two diagrams doesn't matter. So this is due to Johannes Thurston and Zemke. The maps induced by different possible sequences of moves agree up to chain homotopy equivalence. Okay, so not only is this an invariant of the three manifold, it makes sense to talk about CF minus of Y and not CF minus of some particular Heegaard diagram because things are quite natural. Another way of saying that is I can think of the Heegaard Floer invariants as being actual modules and not isomorphism classes of modules. Okay, so this brings us to involutive Heegaard Floer homology. Which was induced by me and Ciprian Manolescu in 2015. Again, adapting some of the ideas in his pin to Szabo Floer theory into the symplectic setting. So, okay, let's
Kristen,
say, yeah.
Can I ask about naturality?
Yeah.
You didn't state the strongest possible thing. Is it because which is some kind of, chain homotopy is unique up to some kind of contractible choice? Is that expected?
So okay, I think I stated first order naturality, and you're asking me if I have infinite order naturality. So you're asking me if the homotopies relating the two maps are appropriately unique.
And I'm pretty sure, yeah, okay, keep going, yes.
And we expect that,
okay.
We expect it's true, but the existing proof of first order naturality hits an obstruction at some point. It comes from surf theory, and there's a point at which you can't go on. So you can't prove it via that method. And as far, it's expected to be true, but but nobody's proved it.
Is the analog and gauge theory known?
Oh yes, I mean Szabo and Floer homology is the homology of a space, or spectrum. So you get all the naturality you want, sort of.
Okay. Thanks.
Okay, yeah. So you might, if you want to take away a moral from this talk, you might think Szabo and Floer homology is more natural, and that's great, and Heegaard Floer homology is more computable, and that's great, and that's why we need both of them in our lives. Or known to be more natural, and okay. So involutive Heegaard Floer homology. So great. So there's an obvious asymmetry in the picture of a Heegaard diagram that I drew you. So maybe I have this one again. And it's the colors of the curves. So an obvious way to get an interesting map of this complex is to switch the colors of the curves and also switch the orientation of the Heegaard surface. That's the same thing as turn your Morse function upside down and then add 3 so it's still self-indexing. All right, so now I have two Heegaard diagrams. I have sigma, alpha, beta, and then the base point. And maybe H bar, which is sigma with the orientation switched, beta, alpha, and then the base point. And if you think about what intersection points and what curves you would count in Lagrangian Floer homology, it will quickly become clear that there's an actual chain isomorphism between the associated complexes. You just count exactly the same things because you switch your orientations and also you switch which Lagrangian was which. And then, well, these are two Heegaard diagrams for the same three manifolds. So by what I said above, I can pick some series of moves on the Heegaard diagram, moves between Heegaard diagrams that will get me back where I started. And okay, so now I'm back to H. And now I have CF minus of some H. And here I just have some chain homotopy equivalence written phi of H bar H conventionally. And that map I don't understand very well at all. That's not a chain isomorphism in general. It's probably complicated. Oh, there's a chat. Mohammed already asked that. Great. Okay, and the composition of these maps is called iota. And Thurston Zemke naturality can be used to show that iota squared is always chain homotopy equivalent to the identity. So this part right here isn't natural, but this part is, and once I've done this twice, once I've done this twice, I get back to something that's covered by naturality, and it has to induce an identity map. Okay, so this gives me a pair CF minus of y together with some map, which is an involution up to chain homotopy equivalence on the pair. And this is unique up to equivariant up to homotopy. Chain homotopy equivalence. Okay, so we have this map, and let me tell you two ways of thinking about this data, if I can. Okay, so first, I can take an actual new theory by incorporating this by building a new chain complex and taking its homology. The chain complex in question will be the cone of the map 1 plus iota on CF minus of y. And this has the algebraic structure of a Z mod 4Z equivariant theory. What that means is that it's a module over the homology of BZ4 and F2 coefficients. What's the 4 in question? It's this 4 right here in pin 2, corresponding to the order 4 subgroup. So Heegaard Floer homology is identified with, in this version, identified with an S1 equivariant version of Cyber-Witten Floer homology. When you take S1 equivariant homology, the order 4 action becomes an order 2 action. The S1 in question is just this S1 right here. And their analog is the analog is the involution iota, and you get a Z mod 4Z theory that way. Okay, another sensible way to think about the theory is just to think about the data of the complex with its map together as a pair. And this is called an iota complex. Okay. And now what are we going to do? It turns out that we could think about, well, what would it mean for two sets of data like this to be equivalent? But one thing it could mean is what we said would be true for any two possible sets of data for the same three manifold. It could mean related by an equivariant up to homotopy chain homotopy equivalence. That is a bad way for me to think if I care about homology cobordism, because homology cobordisms between three manifolds don't induce chain homotopy equivalences on CF minus Y. They simply don't. However, they do introduce another kind of map that I have some control over. Okay, so definition. Two iota complexes, say C1 iota 1 and C2 iota 2, are said to be locally equivalent if there's some F goes from C1 to C2, G goes from C2 to C1, chain maps, which commute with iota up to homotopy, and induce isomorphisms on sufficiently low degrees. Another way of saying that is that they induce isomorphisms on the local homology, the thing I get after localizing after taking U inverse times the chain complex and localizing. Okay, and why would you care about this relation, which is weaker than chain homotopy equivalence? You'd care because this is the relation that gives you a connection to the homology cobordism group. So let I be the set of iota complexes up to the relationship of local equivalence. So this is a big, just algebraically defined group. It's a bunch of chain complexes up to some relation. This is a group under tensor product. And the map from theta 3, there is a map from theta 3 to I, which is to say that integer homology coordinate 3 manifolds go to locally equivalent iota complexes. And this is a homomorphism. So it plays nicely with connected sum. Okay, so now we've mapped theta 3 to a potentially very big algebraically defined group of chain complexes up to some relation. This is a really popular thing to do in low-dimensional topology lately. It's been used to study smooth concordance classes of topologically sliced knots, sort of starting with work of Jen Hom and then continuing into work of lots of other people. Similar constructions have been considered in Cyber-Witt and Floer homology by Matt Stoffregen. One reason this construction is particularly nice is that it plays really nicely with the group relation. The tensor product relationship of complexes here is quite simple and easy to compute. Unlike perhaps the equivalent constructions on the gauge theory side, which have a very complicated relationship, more complicated relationship under connection. So what further computations can you do in this situation? Okay, so we just talked about theta 3 goes to the group of iota complexes up to a reasonable equivalence relation. I can remember I care about the subgroup generated by the Seifert fiber spaces. I can compute what subgroup of iota those generate, and it's a copy of Z infinity. This computation was carried out by Diane Manolescu and Diane Stoffregen. Okay, and then, all right, so, and this splits as that Z infinity and some mystery group. And furthermore, it was Daiham, Stoffregen, and Trong recently took this map and mapped it to a group with a weakened equivalence relationship called almost local equivalence in a reasonable way. And under that, I can map this to the group J hat, which now looks like some Z infinity coming from the subgroup generated by the separate fibered spaces. And it can direct sum with some J prime. Now, why would you do this? It's because once you weaken this relation even further, you get a totally ordered group that you can actually understand extremely well. And in particular, you can give actual examples of chain complexes living here. Okay, so what does the game become at this point? The game becomes realize one of those complexes, one of those examples, by something coming from an actual 3 manifold here, because if you do, that doesn't live in the image of the subgroup generated by the separate fibered spaces, so the 3 manifold must not have either. All right, so all you have to do is find a Y here that maps to your example over here, and then you can go home. Okay, this brings us to section 3, which is what are the tools for doing that? Pause. Are there any questions people want to ask before we go to section 3? Awesome. Okay, so exact triangles and surgery computations. Okay, why is Heegaard Floer homology popular? One reason Heegaard Floer homology is popular is that it's relatively computationally friendly. Okay, so this is by the standards of gauged and Floer theoretic invariance, which maybe isn't saying super a lot. Oh, hi, Ciprian. All right, just checking the chat. Okay. Which isn't, okay, what's one reason for that? There are several different reasons, but one will be particularly important to us today. Is that there is a surgery formula. Okay, what do I mean by that? I mean, if I have a knot sitting inside some 3 manifold, maybe my knots will be sitting inside of S3 for today. I associate to it some Z plus Z filtered FUU inverse complex. Okay, and 2 things are true, which give me a nice result. First, so these are both due to Ozsvath and Szabo. So first, there's what's called a large surgery formula. For n is greater than or equal to twice the genus of the knot, minus 1. 1 shows that HF minus of n surgery on K is determined by CFK infinity of K. And secondly, there is a surgery exact triangle for the theory. And here, to state this correctly, I actually need a completed version of HF minus, and I'll just indicate that by bolding what I'm doing for a moment. So there's a triangle relating for K a framed knot. In a 3-manifold. N surgery on K and N plus N surgery on K and M copies of just the original 3-manifold. And those two things together can be used to prove, for example, that HF minus of N surgery on K is determined by CFK infinity of K. And this gives rise to lots of extremely useful computations because sometimes it's a lot easier to get your hands on knots, and we understand them quite well. So you might ask, what about involutive versions of this whole picture? So in the involutive theory, well, what can I associate to a knot? I can associate to it some, well, I still have CFK infinity. And then if I go back and try rerunning the procedure that produced iota on that chain complex, I will get something called the sum map iota K, which is now order 4 as a filtered chain map on the complex. And you can ask, well, do I have a large surgery formula and do I have a surgery exact triangle? And if so, do I have enough information to just try to figure out the involutive Heegaard Floer homology of my favorite 3-manifold expressed as a surgery off of knowing this information right here about the knot? Okay, so well, question 1, large surgery formula. For n greater than or equal to 2g of k minus 1, HFI minus of n surgery on k is determined by CFK infinity iota k. So Ciprian and I proved that in 2015. And secretly, actually, n greater than or equal to the genus will do because we only care about part of the theory only part of the theory can be interesting, and that part we only need to have n greater than or equal to genus to study. And now surgery triangles, though. Turned out surgery triangles have been for various reasons quite difficult. So, but why would you believe that they do exist? Well, they exist in pin-2 monopole Floer homology. So that's an analog of pin-2 Seiberg-Witten Floer homology defined by Francesco Lim. And he showed that this theory, which is again vaguely analogous to ours, has a surgery triangle in 2015. And previously it was known that there was such an exact triangle for the easier hat theory, HFI hat, using a bordered variation on this whole story that Robert Lipschitz and I wrote down. But okay, so today, the new computational tool, so this is still me and my collaborators, is once again, I'm going to bold this theory to scan for completion, and if you don't think about this theory all the time, you can ignore that, is that there exists a surgery exact triangle for the minus variant of involutive Heegaard Floer homology. Okay, and this leads to, let's say, some computations of CFK of CF minus S3n of k, comma iota as an iota complex, especially when some invariant arising from Heegaard Floer homology called the D invariant or the correction term is equal to 0. This is not determined just by the information in CFK infinity. There are some additional homotopies and complexity going on. And this allows us to do the computation that was asserted at the end of part 1 of this talk. And as a consequence, we get the theorem that I stated there, which I'll restate, which is that there's a Z that lies in the quotient of the homology cobordism group by the group generated by the ciphered fibered spaces. So it turns out that the knot surgery that I mentioned at the beginning of this talk realizes one of the complexes known to lie in this group right here, and therefore it must have come from something here that wasn't in the image of the group of theta 3SF. Okay. And maybe, so how do you get there? The intuition. Okay. The intuition is, remember when I defined the involution, I said there's some sequence of Heegaard mirrors that gives you a chain homotopy equivalence. That sounds very vague, and it's not vague because I'm glossing over lots of things. It's vague because it's pretty non-constructive. So the intuition is construct a more concrete model for the involution, work with perturbations of that. Okay, I see I'm about out of time, which is good because I'm similarly out of words. So thank you all for coming. It was a pleasure speaking to you.
Okay, so let's thank the speaker. So what we usually do is have maybe 10 or 15-minute question section, and then after that, we'll turn off the recording, and if anyone wants to have a more informal discussion, people can stick around. So are there any questions for Kristen?
Yeah, I have a question. So what about rational surgery? Like if I do like P over Q surgery?
You know, yes.
Can you compute, using this method, can you compute CF minus iota?
So the rational surgeries formula is harder to prove and more complicated. So I don't know of any reason these techniques couldn't eventually be used to address it, but we have not gotten to doing that.
Sorry, can you repeat? I didn't hear.
We haven't, proving the rational surgeries formula is harder and more complicated than proving the integer surgeries formula. I don't know of any reason that we couldn't, but we haven't embarked on doing so.
I see. So the improvement with respect to your first paper with the Ciprian is that now you can compute small surgeries.
Yes, now we can compute small surgeries. I agree. Particularly relevant for homology cobordism, since, you know, the homology spheres that are surgeries are +or -1 surgeries, or +or -1/n surgeries, but for integers, +or -1.
So if I want to do 1/n surgery, I cannot with this machinery.
So this machinery cannot solve that problem yet.
I see. Okay. And you think it's like sensibly harder to do that?
Pardon?
It's much harder to do 1/n surgeries than.
Yeah, I think that that's going to be a bunch more work, but I expect it to be true, and I expect if you worked hard enough, but it might be quite a lot of work.
Thank you very much. Actually, also thank you for the very nice talk.
I had a question. At the beginning, you said that the analogous thing to the homology bordism group was PL. rather
Yeah.
than smooth. So could you say something about that? About why that's?
Oh, so the thing that comes up relevantly in the triangulation conjecture is the piecewise linear group, which is why it's the most sensible thing for me to talk about in context. So as I believe was mentioned this morning, the smooth homology cobordism groups aren't trivial by work of Crevere. We were talking about elements of them. But somehow the thing that's relevant for the proof is actually the piecewise linear structures, and it's just that in dimension 3 and 4, those are the same as the smooth structures.
I see. Those are the obstructions that come up when you try to triangulate.
That's right.
Okay, great, thanks.
I'm gonna stop screen sharing now.
So maybe I have another question.
Yeah.
So in many applications, or okay, in basically all the examples I know, when you do 1/n surgery on a knot, then it's hard to distinguish them using correction terms and stuff like this. I mean, do you expect that if I have a knot and I do 1/n surgery, then all the guys, all the CF minus iotas I get are locally equivalent?
No, I definitely don't expect that, because I expect that odd denominator surgeries and even denominator surgeries behave differently. Why do I expect that? It's known to happen in pin-2 monopole Floer homology. And if you sort of take a look at the Heegaard Floer surgery complexes, it falls out that even denominator surgeries, nothing really interesting can happen. The complexes just look different. So.
Okay. Thank you.
Nice to meet you in person, by the way. I don't know that we have.
Any other questions? Actually, I have one. Oh, sorry. Go ahead.
I'd like to see some of the proof, but that might lead us too far away, so it's not.
I can tell you what the model for the involution is. Would you be happy with that? Let me draw that picture. That I can do real quick, and maybe it'll be a little bit satisfactory. Assuming I can get Zoom to do that. Hang on just a sec. Okay. So the intuition is, in general, it's quite hard to get your hands on iota, but here's a model that's useful. So let's say I have a Heegaard diagram. And my Heegaard diagram will have, a red curve and a blue curve. It'll be a boring Heegaard diagram. And it can be H. And the idea is we're going to double this Heegaard diagram. What does that mean? You take the connect sum of the diagram with its opposite connected by a tube. In practice, that means I take the alpha curves and I draw them over here. I take the beta curves and I turn them over into alpha curves on the other side. And then I add a standard set of curves for the bordered Heegaard diagram. I could state that for you properly homologically, but you've seen bordered Heegaard diagrams, you know what that means. And this is the so-called double of the Heegaard diagram. Actually, the double, there's an asymmetry in whether I make these curves alpha, the original curves alphas or betas, so let's call it dA. Okay, and it turns out that the map that goes from, there's a cobordism map consisting of canceling 1 and 2 handles that goes from CF minus of H to CF minus of the doubled Heegaard diagram. But H and H bar, its opposite Heegaard diagram, have the same double. So I can get over to H bar. And the map that goes from, there's a map, that cobordism map that goes from CF minus dA of H to CF minus of, this is now H bar. So there should of course be base points the whole way through. And this will be sigma.
I'm slightly confused.
Yeah.
I mean, H and H bar should give, I mean, in my mind, I see rather than the same diagram, a diagram which is the same after you flip it like that.
Yeah, but those things are the same. You end up with equivalent diagrams.
Okay.
So this is on a surface that looks like sigma connects sigma bar. So in particular, I also understand this map quite well. And this is the model for the chain homotopy equivalence between H and H, between CF minus of H and CF minus of H bar that we use. So, and it turns out, well, we actually use some variant on this, but this is the central idea. And it turns out that this is much better than work with arbitrary chain homotopy equivalence. This actually gives you a chance of getting your hands on the map. Whereupon we were able to actually start producing the maps that you would need in order to get a surgery exact triangle.
And then the map are the usual ones, or you have to do something different for?
Say what you mean? Sorry, say again. I didn't quite understand that.
Then the map that you construct for the triangle.
Oh, yeah. So like I said, we don't use exactly this map. We use a slight variation of it, but the triangle maps are always the things you expect. And then you also have to keep track of, what do I want, right? If I want an exact triangle, well, I would ordinarily want a shared exact sequence of chain complexes. And then I also have the maps iota. And what do I need in order to get an exact triangle of the involutive homologies? Well, firstly, I need to have chain homotopy equivalences here, which is to say I need iota to homotopy commute with this whole thing. And maybe this isn't an exact triangle, so I also have chain homotopy equivalences here. And then I need one that goes all the way through the entire thing that makes the whole thing homotopy commute if I expect to actually get what's an exact triangle. It's an equivalence between this iota complex and the cone of these iota complexes.
Yes.
So I need to have all those maps. So I end up counting, things that are more complicated than triangles.
Okay.
For example, so the cone of 2 iota complexes is not even an iota complex without all these maps. Like, you can just write down ones where that's not true, and what the homotopy is affects the homology, and yeah, so there are more maps you have to keep track of.
Oh, okay.
I'm gonna erase this messy part from the public notebook.
Any other questions? So maybe I'll go ahead and turn off the recording, and then people should feel free to stick around and have a more informal discussion.